In problems 12 through 16, I'm trying to concentrate on your ability to solve trigonometric equations. So you notice I grouped these together on the test here, 12 through 16. All of them need to be solved for values of the angles between 0 and 2 pi, 1 revolution of the unit circle. No need to include 2 pi since it is coterminal to 0. When I look at what I've done on those problems, you'll see here in the first one, it gave me the sine of x is the square root of 2 over 2. The square root of 2 over 2 as a decimal is like 0.707. So I'm thinking all this is asking me is when is the y value approximately 0.707 on the unit circle? And I can say, well, all I would have to do is think of a unit circle. 0.7 is a little more than 2/3 of the way between 0 and 1, approximately right here. So there's a y component in quadrant 1 and quadrant 2 that gives me that. And of course, you already know, hey, the sine of pi over 4 is the square root of 2 over 2. Yeah, the y component on the unit circle at that point is approximately 0.707. Same thing happens at the angle that splits quadrant 2, 3 pi over 4. So we can quickly see our two solutions to that problem are pi over 4 and 3 pi over 4. Now for the next problem here, we're looking at it and it's giving us the square root of 3 tangent x minus 1 is equal to 0. So of course we move the 1 over to the right hand side and then divide it by the coefficient of x, that's square root of 3. That gives me the tangent of x is equal to positive 1 over the root of 3. Now, this is just asking you, when is the tangent function equal to 1 over the root of 3? So that's when the ratio of the sine to the cosine has to change more than the sine changes. So I can say, well, I know that the square root of 3 is like 1.732. So this is when the cosine goes to the right 73% more than the sine would go up, or when the cosine goes to the left 73% more than the sine would go down. In either one of those scenarios, the ratio would be 1 over the root of 3. And I can say, well, the only time that the cosine goes out more than the sine would go up in quadrant 1 is at an angle of pi over 6. At that point, my cosine is the square root of 3 over 2, and my sine is 1/2. Sine over cosine, 1 over the root of 3. And then at 7 pi over 6 in quadrant 3, you can say, well, your cosine moves to the left, the negative square root of 3 over 2. Your sine only moves down negative 1/2. So you say, again, it's going to be the ratio of 1 over the root of 3. So I get pi over 6 and 7 pi over 6 as my only two answers on the unit circle. Up next, I'm looking at the cosine of 3x is equal to negative 1/2. I need you to remember that this is the problem and where you're going to have to think of the multiple revolutions of the unit circle. Anytime you have a number multiplying the angle on the inside, then you have to think about it just like this. In the instructions, it said that the angle, in this case x, had to be between 0 and 2 pi. But that means 3x could be between 0 and 6 pi because that's going to be 3 times the angle x. So if x has to be some angle between 0 and 2 pi, then the angle inside of this cosine function could be between 0 and 6 pi. So in other words, I'm just thinking 3 revolutions of the unit circle. I need to be thinking of what values at which the cosine is equal to negative 1/2. So I can say, well, that's just when the x component on the unit circle is negative 1/2. That occurs at 2 pi over 3 in quadrant 2, and at pi plus pi over 3, or at 4 pi over 3 in quadrant 3. So within my first revolution of the unit circle, I would easily know, hey, these two are my angles, but that's not enough. Because of that multiplicity on the angle, you have to think of multiple revolutions. So you just say, oh, okay, that same cosine is going to be negative 1/2 at the point where the angle is at that same point in the second revolution. So just add 2 pi. 2 pi is the same thing as 6 pi over 3. So we say 2 pi over 3 plus 6 pi over 3 is 8 pi over 3. I did the same thing to get to this. That same value, the cosine would equal negative 1/2 on the third revolution at this angle too. So add another 6 pi over 3 to get to 14 pi over 3. Same thing down here at the angle in quadrant 3 that satisfies the criteria. We know 4 pi over 3 is the angle in the first revolution. In the second revolution, coterminal to that, add 6 pi over 3, you get to 10 pi over 3. Add 6 pi over 3 again to get to the third coterminal angle, and you're at 16 pi over 3. Now, this tells me that that angle 3x could be any one of these 6 possible values. I go from low to high. 3x is equal to 2 pi over 3, 4 pi over 3, 8 pi over 3, 10 pi over 3, 14 pi over 3, and finally 16 pi over 3. Now, in order to solve for the angle x, we just say, well, simply divide by 3 everywhere. And you see all of my angles for the final solution are angles that sit between 0 and 2 pi. 18 pi over 9 would be 2 pi. So all of these are between 0 and 2 pi, and they would all satisfy the criteria of the problem. Nice final answer. Now, number 15, I'm trying to make sure in each one of these problems, I'm getting one of the major concepts of solving equations. Here I'm doing the multiple angles. In these first two, those are supposed to be a little bit more simple problems to where you're just thinking about where the sine, cosine, and tangent are on the unit circle. Now in number 15, you'll be forced to use one of your Pythagorean identities to put it all in terms of one trig function. So if I give you 2 cosine squared x plus 3 sine of x is equal to 0, you're supposed to understand from the very beginning of this problem that you can't work it in its current format. You need to get it all in terms of the same trig function. Well, I know that cosine squared is equal to 1 minus sine squared. So then I can say, well, all right, then my first, after I distribute that 2 through there, I'll get 2 minus 2 sine squared x plus 3 sine x is equal to 0. Now I can see that this can be written as a quadratic function in terms of sine. I would prefer the leading term, the squared term, to be positive. So I went ahead and wrote it in descending order and multiplied both sides by -1 from this step to this step. Obviously, 0 multiplied by -1, still 0. But now I need to change the sign of every term on the left. So I have positive 2 sine squared x minus 3 sine of x, and then minus 2. Now, quadratic form, I go ahead and set up my my quadratic factors. This is the term ax squared plus bx plus c. So I just say, well, trinomial factorization. I know the first term, the only terms possible that can multiply to get 2 sine squared x is 2 sine x times the sine x. And then I had to think, well, the last term had to be factors of -2. The only factors of -2 are -2 and 1. It's just I had to determine where did the -2 go, where did the 1 go. I knew that the -2 had to go over here because it had to multiply the 2 sine x. 2 sine x times -2 gives me minus 4 sine x. Then I would have the plus 1 here plus sine x for a total of minus 3 sine x. So this I know is the correct factorization. Once you have it factored, you use the zero product property, set each of those factors equal to 0. Okay, well, sine x minus 2 is equal to 0. That gives me, when I set that equal to 0, I get the sine of x is equal to positive 2. But you know, that's not possible. Now, sometimes that causes confusion. As soon as like, oh no, I must have done something wrong. No, we've done everything correct. It's just that factor does not contribute to a solution in this problem. And that's okay. The sine of x can never go above 1. It can't equal 2. And so I go to the other factor and say, well, then the other factor must be able to equal 0 in order for this to have a solution. If the other factor is equal to 0, then 2 sine x is going to equal -1. Sine x would equal -1/2. And so now you're just thinking, well, okay, all I need to think about is when is the y value on the unit circle equal to a -1/2? That's going to occur at 7 pi over 6 and 11 pi over 6. Thus, that's your two answers for this problem. In the next one, I want you to see again, this is a factoring problem. Instead of trinomial factorization after using an identity in 15, in this one, it's set up to where you just use the greatest common factor in the very beginning. I see the first term and second term have a factor of sine x. I factor that out. When I do, I'll have sine x times the group tangent x minus 1 is equal to 0. Now the zero product property tells me I need to set the first factor equal to 0 and the second factor equal to 0. If the first factor is equal to 0, then I get the sine of x is 0. So that's only asking you, when is the y component on your unit circle equal to 0? That's at an angle of 0 and pi. So I already get those two answers. Now my other solution comes from when the tangent of x is going to equal 1. And so I think, well, the tangent of x is 1 when the sine and cosine are the exact same value. That occurs at pi over 4 and 5 pi over 4. It would be okay to leave your answer as two separate solutions like this, and I would know that all of that's your solution. It'd be even better if you pulled it all together and say, well, all of the solutions from low to high, 0, pi over 4, pi, and then 5 pi over 4. All four of those are solutions to number 16. Now, after that, that in 16 finishes chapter 5. We move to chapter 6 problems, and the first topic in chapter 6 was the law of sines. In 17, I asked you to use the law of sines to solve the following triangle with the given information. So I give you angle A is 42, angle C is 96, side C is 12. And I ask you to round sides to 1 decimal place. Okay, so you'll notice that I do not give you the law of sines or the law of cosines on this test. Those two formulas need to be known on this test, and really they're easy to memorize. So you really should know them in every math class going forward. For the law of sines, first thing I did was I put down the information I had. I had A and C, and I think I had, which of the sides I had, side C given. So I had that information given. Now, the first thing I did, obviously, if you're given two angles, you can easily find the other angles by saying, well, we know the angles inside of a triangle have to add up to be 180 degrees. So I took 180 minus the two angles given, and I knew that the remaining angle also had to be 42 degrees. Now, I doubt that the problem on your test will have angle A equaling angle B. This is an isosceles triangle, but whether it's not, whether it is or isn't, you can still use the law of sines to solve for your other sides. So at that point, since I had side C and I knew all of my angles, I decided, well, I'm going to find side A. And I knew since angle A and angle B were the same, whatever I get for A also is the answer for B. Now, if these were different angles, I would have to do yet another step to find B. But the law of sines says that the ratio of any side divided by the sine of its angle has to be proportional with any other side in the sine of its angle. So I took A over the sine of 42 is equal to 12 divided by the sine of 96. Okay, now solving for A, I just said, well, I'm going to multiply by the sine of 42 on both sides of this equation, and I'll get A is equal to 12 sine 42 over the sine of 96. And at that point, you just enter that into your calculator. Please make sure you're in degree mode, and you'll get approximately 8.1. Now, units were never given on this problem, so it's just 8.1. And I went ahead and put that in for B. Now, had A and B been different angles, I would have had to have done another step and said B divided by the sine of its angle is equal to 12 over the sine of 96 and done the same solution process. But that just wasn't necessary here. Now, number 18. Number 18 is our law of cosines problem. It's given to you in a word problem format. It says two cars leave a city at the same time and travel along straight highways that differ in direction by 60 degrees. One car averages 75 miles per hour, and the other averages 66 miles an hour. We're supposed to find out how far apart will the cars be after 20 minutes. So we know we can't use the law of sines because we don't have an angle opposite a side that we know. That's okay. Law of cosines will work flawlessly. So here's where I said the cars are leaving this point at an angle of 60 degrees. One car is going to travel. Now, it doesn't matter whether you label the top one 75 miles per hour or the bottom one. It's irrelevant as long as you show that the angle between them is 60 degrees. I labeled this bottom side, the person traveling 75 miles per hour for 20 minutes. Now, you can just say, well, 20 minutes, that's 1/3 of an hour. 75 miles per hour for 1/3 of an hour, that distance is going to be 25 miles. Now, the other person is traveling and averaging 66 miles per hour, again for 20 minutes. Now, I showed it as 20 over 60 instead of 1/3 of an hour, because what if I gave you something weird like 23 minutes? It's no big deal. You would just say 66 times 23 over 60, because that's the portion of an hour it would be. In this case, it's 1/3 of an hour. That made the math really simple. 66 divided by 3 gives me 22 miles in this direction. So 22 miles and 25 miles, the angle between them is 60 degrees. We're supposed to find the distance after 20 minutes. Okay, so I labeled my other side x, and I can say any side of a triangle squared is equal to the sum of the squares of the other two sides. So I said 25 squared plus 22 squared minus twice the product of the other two sides. So minus 2 times 25 times 22 times the cosine of the angle opposite the side you're looking for. So minus 2 times 25 times 22 times the cosine of 60 degrees. Now this problem, the numbers work pretty easily. 25 squared is 625, 22 squared is 484. Here we have 50 times 22. 50 times 22 is going to give me minus 1100. And I know that the cosine of 60 degrees, that's just going to give me 1/2. So I'll have my 625 plus 484 minus 550. That's going to give me 559. But I know that that's equal to x squared. X, of course, is the positive square root of that. And that's where you go to your calculator. And I didn't say how far to round here, so I'm really not going to be too hypercritical. But anytime you're not stipulated how far you should round, the general rule of thumb is 3 decimal place accuracy. So that's what I stuck with here. Since I did not stipulate how much you should round, 3 decimal places is understood. So I got 23.643 miles is the distance after 20 minutes. Now for our next problem here. Here we get into the polar coordinates. This would be section 6.3. It's asking us to find another representation for the polar coordinate 8, pi over 6 that satisfy the following requirements. The first one, we need r to be positive, and we need our angle to be between 2 pi and 4 pi. So I'm thinking, okay, then that means if r is positive, it still has to be 8. I just need to find the coterminal angle to pi over 6, 1 revolution beyond pi over 6. You'd say, well, that's pi over 6 plus 2 pi. That's the same thing as pi over 6 plus 12 pi over 6. I get to 13 pi over 6. And you'll see that's precisely what I did. The value that has a positive r value, if it's a positive r value, it has to be the same as the existing r value in this problem. And the theta had to be between 2 pi and 4 pi. So coterminal angle to this, just add 2 pi and you get that. Now for your second one. In the second one, or for part B, it's wanting a negative value for r and theta to be between 0 and 2 pi. So you just say, well, if I have to have a negative value for r, it has to be the opposite of r. So I have to say, well, -8. Now, it needs to still be at this same point. So then you can just say, well, if the R value is negative, you need to go to the opposite side of where the unit circle would be, and that's going to be at 7 pi over 6. So if you go in a direction of 7 pi over 6, but your R value is negative 8, it's going to put you back up there at the same point as 8 pi over 6. Gorgeous. Now for our last one here, I still want a positive R value, so you know R is going to be 8, but now your theta value has to be negative. So this is very similar to the first one, except now instead of finding a coterminal angle that's 2 pi radians to the right, you'll find a coterminal angle that's 2 pi radians to the left. So you just say, well, subtract 2 pi from pi over 6. That's pi over 6 minus 12 pi over 6 gives you negative 11 pi over 6. And I know that if I plot out 8 comma negative 11 pi over 6, it's the same point in polar form as the ordered pair 8 pi over 6. That's all we have to do with number 19. Number 20 gets us into vectors. And you'll see here on this number 20, we're looking at, it says, if vector v has initial point negative 2, 5, and terminal point 7, 8, vector w has initial point 12, 3, and terminal point 6, 6. Find the following. So I need the component forms of vector v and w, and then we do some vector operations, find 5 times vector v minus 2w, and then we want to calculate the magnitude of twice vector w. Okay, no problem. So all I have to do for vector v, it's the change in the horizontal component times I plus the change in the vertical component times j. Well, that horizontal component, 7 minus negative 2. All I had to do there was just say, well, it's this x1 minus this x1, 7 minus negative 2. And then the y component, that's the coefficient of j, it's going to be 8 minus 5. That's where this came from. So I can say, all right, that's going to be, it's moving 9 units to the right and 3 units up. So I get 9i plus 3j. Similarly, for vector w, I would say, well, it's going to be x2 minus x1 is the coefficients of I. And you can see, well, my coefficients of I, it's going to be 6 minus 12 for the coefficient of I. And then the coefficient of j, I have 6 minus 3. That's because that's y2 minus y1, 6 minus 3. And so I can see, okay, for vector w, what does it do? It moves an object 6 units to the left and 3 units up. Thus, its vector format is negative 6i plus 3j. Now, if you're finding 5v minus 2w, you simply take the scalar multiple of 5 times v. You get 45i plus 15j. And then we're going to subtract from that 2 times vector w. So I left my minus sign in there, multiplied vector w by 2 to get negative 12i plus 6j. Now I need to subtract that from 5v. 45i minus a negative 12i gives me positive 57i. And then 15j minus 6j gives me 9j. The combined resultant vector of 5v minus 2w is 57i plus 9j. Now, the magnitude of 2w, you could have went ahead and multiplied w out by 2 and then taken the magnitude. I'm using an identity that says, well, the magnitude of 2w is the same thing as 2 times the magnitude of w. Now, what is the magnitude of w? It's just the square root of its horizontal component squared plus its vertical component squared. So you'd say, okay, then I'll say it's 2 on the square root of negative 6 squared plus 3 squared. Negative 6 squared is 36, 3 squared is 9. When I add that together, 36 plus 9 is 45. Now, I simplified this. I knew 9 times 5 is 45. So the square root of 45 simplified to be the square root of 9 times the square root of 5. Square root of 9 is 3. 2 times 3 is 6. The best answer would be 6 on the root of 5 here. Final answer. Now, for the next problem, it's a little bit more involved. with the vector applications. Says you have two forces, F1 and F2, of magnitude 10 and 30 pounds, respectively, that are acting on an object. Now, the direction of F1 is 20 degrees east of north, and the direction of F2 is 65 degrees east of north. We're supposed to find the magnitude of the resultant force, and then after you do that, the direction of the resultant force. The resultant force, of course, being F1 and F2 combined. Okay, so I went ahead, tried to show my work here really well. Here's my first force. It's acting at 20 degrees east of north. Well, if it's acting at 20 degrees east of north, then the angle theta, which is always the angle from your positive x-axis, you can say, well, my angle theta is 70 degrees here. So force F1, what's the horizontal component of that force? It is always going to be whatever the force is times the cosine of theta. So you say, well, the horizontal component is going to be 10 cosine theta. That's the coefficient of I. The vertical component is always the force times the sine of theta. So I get 10 times the sine of 70 degrees as the coefficient of J. You go to your calculator, and of course, here you would expect the horizontal component to be less than the vertical because it's pulling up a lot more than it's pulling to the right. And we can see that. It's pulling to the right with a force of 3.42 pounds of force, and it's pulling up with a force of 9.397 pounds of force. So I can see much more vertical movement than horizontal movement due to force 1. Now, what about the vector that's resulting from the force F2? Well, F2, it said the direction was 65 degrees east of north. So that means this angle right here is 65, meaning the angle within my quadrant is going to be 25 for theta. That's the angle between the positive x-axis and my force. So I can say, okay, well, what's the horizontal component of that force? It's the magnitude of the force times the cosine of theta. So the coefficient of I is 30 cosine 25. The coefficient of J, the vertical component, is going to be 30 times the sine of the angle theta, which is again 25. 30 times the cosine of 25 degrees. And I would round to 3 decimal places within the problem. I had 27.189. Now, it should make sense that you're getting much more horizontal pull on this one than you will vertical because it's pulling to the right more than it's pulling up. The vertical force, thanks to F2, is going to be 30 sine of 25, and that gave me 12.697 out of that component force of 30 pounds. Now, the resultant vector, or when you combine force 1, that's 10 pounds of force, and force 2, that's 30 pounds of force, you just add their two vectors, and you can say, well, the horizontal component is going to be 3.42 plus 27.189. I'm getting 30.609. The vertical component, 9.397 plus 12.679, I get 22.076. So now this is my resultant vector. I'm finally ready to answer my questions. With question A, what is the magnitude of the resultant force? Please remember the magnitude of the force vector, in this case F1, F2, the resultant force, is just the square root of the horizontal component squared plus the vertical component squared. So when I do this and I round to, I believe I rounded mine to 3 decimal places and it just rounded off to that, I had 37.74 pounds here. Now, when I found the angle or the direction of the angle, find the direction of the resultant force. Now notice I didn't say I didn't ask you to find the bearing, though you could if you wanted to, that'd be cool. I just asked for the direction. Anytime you're asked for the direction, that's the angle theta from the initial x-axis. Now, this case, it's going to be easy because your tangent of theta will give you the angle that you need. We're not in any other quadrant, and you know that the tangent of theta, or the inverse tangent, is defined from negative pi over 2 to pi over 2. So my angle that's going to be in quadrant 1, tangent theta, and the inverse tangent, it's going to give it to me directly. I don't have to think about where it would be in any other quadrant. All I have to do is say the tangent of theta is always equal to the vertical divided by the horizontal. So that's the 22.076 divided by 30.609. Thus, I can say, well, then my angle theta is the inverse tangent of that ratio, and I get 35.8 degrees. And now that should make sense to you. This angle was at 25, the other angle was at 70, but the angle at 25 was 3 times the magnitude of the force at 70 degrees. So you knew that it was going to be much closer to 25 than it was going to be to 70, and it is. The overall angle direction is 35.8 degrees from the initial x-axis. Okay, for our next problem, we're moving away from vectors and moving towards complex numbers. And in 22, I'm asking you to use De Moivre's theorem to find the power of a complex number. I've decided I'm not going to ask you to use De Moivre's theorem to find roots of complex numbers. It'll just be the powers. So since I'm giving you, or since I'm not giving you the roots and asking you for the powers, and the formula for powers is so easy, I'm not putting that formula on the test. So you have to know, anytime you raise a complex number in polar form, then all you have to do is raise the R value out in front to that power, and then multiply each of your angles on the inside by that power. So if I have the complex number 3 times the group, cosine pi over 12 plus I sine pi over 12, then I can just say, well, all right, all I have to do is raise 3 to the 4th power, and then inside my group, it's going to be the cosine of n times the angle. In this case, that's going to be 4 times the angle. Pi over 12 gives me 4 pi over 12, plus I sine of 4 times the angle, 4 pi over 12. Now, 3 to the 4th power, that's the same thing as 9 times 9, 81. My angles on the inside, I know 4 pi over 12 reduces down to pi over 3, so I just said my inside is going to be cosine pi over 3 plus I sine of pi over 3. Now, if I asked you to leave the answer in polar form, you would stop there. The chances of that are slim to none, though. I will ask you to put the answer in rectangular form. Rectangular form of a complex number is always z is equal to a plus b times I. So you say, okay, I need to get rid of polar form. No problem. I'll evaluate the inside. Cosine at pi over 3, that's the cosine at 60 degrees or pi over 3 radians, 1/2. The sine of pi over 3, that's the square root of 3 over 2. So then all I have to do is take my 81, distribute it through this group, 81 times 1/2, 81 over 2. That's your real number component of your complex number. Now, plus b times I. So I can say, well, the coefficient of I is going to be 81 times the square root of 3 over 2, gives me plus 81 on the square root of 3 over 2, all times your imaginary number I. This is your final rectangular form answer, a plus b times I. I will want that format for your complex number final answer. The last problem, or nope, 2 more problems, sorry. Problem 23. It's asking us to find the angle between a vector 3i minus 2j and another vector w, negative I plus 4j, round answer to the nearest 10th of a degree. This is where I'm trying to get you to use the dot product. This is the very last section, section 6.7. I do put this formula on the test. You'll notice it says find the angle between 2 vectors. You have the angle between 2 vectors formula. Your formula for that is that the cosine of theta is equal to the dot product of the vectors divided by the magnitude of the vectors. So now I go to my problem. Here's my 2 vectors, v and w. The cosine of theta should equal the dot product divided by the magnitude of the product of the magnitudes. So the dot product of V times W, we just say, well, okay, it's going to be the horizontal coefficients multiplied 3 times -1 plus the vertical coefficients multiplied -2 times 4. So I get 3 times -1 plus -2 times 4. My numerator is going to give me -3 plus a -8. It's a -11. Now, the magnitude of vector V, it's just the square root of the horizontal component squared plus the vertical component squared. You can see here I did, well, it's going to be 3 squared plus 2 squared. Remember, 2 squared and -2 squared, same thing. So there's no need to put a -2 in there. And then same thing over here. The magnitude of W is going to be the square root of -1 squared plus 4 squared. It's the same thing as 1 squared plus 4 squared. So in my denominator, I'm getting the square root of 13 times the square root of 17. I just multiplied 13 and 17. That gives me the square root of 221. So now I know that the cosine of theta is equal to -11 over the square root of 221. Instantly, I knew that this was an obtuse angle between the two vectors, because anytime the cosine is negative, that tells you that you're in quadrant 2. The cosine is always positive between 0 and 90 degrees. Now, I said I wanted a degree answer to the nearest tenth of a degree, so you need to make sure your calculator is in degree mode. So I'll show that here, degree mode. And then it's as simple as just saying theta is equal to the inverse cosine of -11 divided by the square root of 221. Boom. You get your 137.7 degrees rounded to the nearest tenth of a degree. And then your last problem here. It's an application problem, but it's a pretty quick one. It says you have a sled is pulled along level ground by exerting a force of 30 pounds on a rope that makes an angle of 35 degrees with the horizontal. How much work is done by pulling the sled 200 feet? So work is going to equal force times distance. Now, the force is not how hard you're pulling the rope, though. It's the resulting force on the object. So you say, okay, then the force in that horizontal direction, horizontal force is always given by cosine. You can just say, oh, then it's going to be 30 cosine of 35 degrees. And then the distance is your 200 feet. Well, please notice, yeah, your work is going to equal the magnitude of the force times the distance times your cosine of theta. So that in this case, it's really the distance is 200. The resulting horizontal force is 30 cosine of 35 degrees. Whenever you multiply all that out, you should get 4,914. And again, I didn't say how far to round your answer. So the rule of thumb is always 3 decimal places. I put 0.912 here. If I show that here on the calculator, I just have 30 times 200 cosine of 35 degrees. Boom, the 4,914.912. And now the units, since this is an application, I do want units here. This was moved a distance of 200 feet and the force was in pounds. So your final answer is the work is 4,914.912 foot-pounds. And also, please make sure any degree answer has the degree sign. Otherwise, it's implied to be radians, which would be wrong. I don't want you to miss cheap points of not putting units whenever they need to be there. Okay, guys, let me know if you have any questions. I look forward to seeing you to where you can take this fun test. It's a pretty long one, but I think it's a good one. Again, let me know if you have any questions. I'll be glad to help.